in order to understand the computational complexity of merge sort, we're going to use the logarithmic function. And just as a reminder, the logarithms that we're using are base 2. So a logarithm function to the base of 2 means how many times do you have to divide a number by 2 in order to get down to 1. In the case of merge sort, this makes sense because at each recursive level we are splitting the input array into half. So essentially we are performing 2 recursive calls on half the original input size at each level. So this has the meaning that if a recursive algorithm is well designed, it tends to run faster because you're basically splitting your original problem into smaller subproblems in recursion. And your tree has a height which is logarithmic. And this means that your runtime increases very slowly with the input size. So you can see in this example that the logarithm of 32 is 5, and the rationale is that if you would have to split 32 in half 5 times, you would get down to 1. And the logarithm of 64 is 6, because you would have to split 64 into half 6 times before you would get down to 1. And the connection to merge sort is that you would have to split the input array into half that many times before you would get down to the base case where your arrays had a size of 1 element. So you can easily see from this illustration that the merge sort algorithm is significantly faster than either insertion sort or selection sort, because those had runtime which was quadratic. In other words, it was bounded from above by the function of x to the power of 2, where x was the size of the input dataset. While merge sort has an upper bound of x times log x, where x is the size of the input dataset. Now we will explain next how this x times log x upper bound is derived for merge sort. But first let's do a proof of correctness. So if you wanted to prove the correctness, you could do this by induction. Here your inductive hypothesis would be that in every recursive call on an array of length n, merge sort is returning a sorted array. So your base case obviously holds because a single element array is always sorted. Now your inductive step is that if L and R are sorted, then that means that the result of L and R is always sorted. And this is easy to solve because the merge function simply loops through the left and the R subarrays and places each element in the correct position in the original array. And from this you can conclude that in the topmost recursive call, after the recursion completes, merge sort will give you a fully sorted array. Now, as far as the runtime is concerned, we have claimed that merge sort has an upper bound of n log n, where n is the size of the input dataset. This is derived from c times n times log n plus c times n. Now, how is this derived? You have to understand that merge sort is basically a recursion tree, and the tree has a height of log n, where the height is essentially the number of edges in the recursive tree from top to bottom. And then the number of levels is log of n plus 1, where the number of levels is the number of the nodes from the top to the bottom. And the nodes are the recursive function calls which get placed on the runtime stack, and then the edges are simply recursive function calls on a smaller data set. So at the very bottom of this recursion tree, you have n leaves, which are simply problems of size 1. In other words, they are single-sized arrays that are already sorted. Now this figure from CLRS shows you that because at each level of the tree we have a constant amount of work that involves some housekeeping, like breaking up the array into subarrays and tasks like that, and initializing arrays in memory. And at this recursive level, your problem size gets reduced by half, and at the next level it also gets reduced by 2, and at the next level it gets cut by half. So if you look at this tree level wise, at each level of this tree, the amount of work is performed is Cn, because at the top level, at the root level, you perform Cn work, and then at the next level you perform 2 times C times n over 2 work, which is C times n, and then at the bottom level of the tree you have one single element at each array, and therefore you have C times n amount of work. Now in order to compute how much work is done in total by this tree, you have to multiply Cn times the number of levels in the tree, and the number of levels in the tree is log n plus 1. So Cn times log n plus 1 equals Cn times log n plus Cn. And from this it's easy to derive that the upper bound on the runtime is theta of n log n. So we can easily conclude that merge sort is faster than insertion sort, which had an upper bound of big O of n to the power of 2. And that means that its worst case runtime has a lower order of growth than insertion sort. Merge sort's upper bound grows significantly slower than insertion sort's upper bound, and you can easily see this by plotting the functions x squared versus x times log base 2 of x, which was the upper bound of insertion sort versus the upper bound of merge sort. And you can see that that for insertion sort it grows very quickly, while for the case of merge sort, x times log x grows much more slowly than insertion sort. And just keep in mind that these are actually the upper bounds, so they provide an upper bound on the runtime of each algorithm. And another important point is that for the case of merge sort, all of the best case and worst case runtimes are in fact n log n, because regardless of how your input array is sorted, the same amount of work is involved, because you need to split the array at each level in half and then merge the subarray. So even if you have pre-sorted array, that's not going to affect your upper bound. While for the case of insertion sort, we discussed that it was actually the best case you could have, where your array was pre-sorted, but this is not the case for merge sort. And that's an important point, because even though we usually talk about the worst case complexity of algorithms, there can be some occasions where the best case complexity can actually differ between algorithms. Then the question becomes, how likely are we to actually encounter the best cases? For example, will we actually encounter those utopian datasets frequently, or is it unrealistic to expect those ideal datasets to actually appear in the real world? So I have explained this cumbersome analysis that we do in order to analyze the running time of merge sort. But actually, you don't have to do this cumbersome and tiring analysis every time that you want to analyze the runtime of a recursive function. There's actually a very convenient theorem called the master theorem, which allows you to deduce the upper bounds and lower bounds on your computational complexity for a divide and conquer algorithm if you simply know the constants. Like, for example, how many subproblems does your original problem get broken up into at each level, and by what factor does the problem get reduced at each level? And if you just know those constants for divide and conquer, then you can easily extract the upper bound on the algorithm for your recursive functions. So for merge sort, for example, if we know that the input size gets split in half at each recursive call, and we have two recursive calls at each level, then the master theorem, which I will explain next time, allows us to easily extract that the runtime for merge sort is big theta of n log n.